So we talked about ultrasonic sensors, right? We talked about capacitive and inductive sensors. Are you okay with those guys? We talked about pressure. Did we talk about pressure switches? And this is not a very good slide. I need to try to make my picture a little bigger without getting into my. There we go. That's about the best I can do. We have different types of pressure switches, and it's really not important for understanding exactly how they work. So what does a pressure switch do? I've got all my sensors over there. What does a pressure switch do?
You can set the pressure you want at some number.
Sometimes you can. Ability to set when it turns on and when it turns off. I can set the pressure that it delivers to the system, right? Y'all understand that? So this right here cuts off at 100 psi and cuts on at 70, which is standard for most compressors that run a tank. So a compressor that runs a tank, what we do is we feed off the tank. If we get below 70, then what happens? The compressor cuts on. When we get up to 100, what does it do? Cuts off. And that's why when you run your tools, normally your tools run, most pneumatic tools run at about 70 psi. 60 psi. So that gives you a pretty good deal of time. So you got a little leeway there. So right. So if your compressor runs between 70 and 100 and your tools run at 60, then you can set your pressure regulator for 60 and you'll always have air. If you're not using a tool that exceeds the flow rate of your compressor. So if you empty your tank and then you're trying to get it off your compressor, then your compressor will never build up that pressure. Your compressor runs all the time, which is not good because then your motor will burn up. So most compressors use what they call intermediate motors, which those motors are not designed to run 24 hours a day, 7 days a week. They're designed to do what? You hear that little compressor over there? You got to hear this big compressor in here, which hopefully it don't cut on because it makes a lot of noise. But it works like that. So a lot of your shop compressors work on this same principle. So I don't get to set where it cuts on and where it cuts off. But I do have a pressure regulator on it. So don't get pressure switch confused with a pressure regulator, right? You understand? This is a pressure switch. Well, actually, the switching mechanism is gone. But this is using a device called a board-on tube. So this is the sensing element right here. It runs around. This camera is extremely slow, guys. But it runs around the outside. And what happens is my pressure comes into here. And then when pressure comes in, what will the pressure try to do with this big metal tube that's in a C? It's in the shape of a C. What will it try to do? It's going to try to straighten out. It's just like those things that we buy for birthday parties for little kids. It's got the spring in there. So that's a board-on. You're looking at a board-on tube. So when you blow on it, what happens? It uncurls, and as soon as you take the pressure off, it does what? Curls back up. That's a board-on tube. All we're doing on this one, we got a very limited range, but I can move it. And of course, when I move the board-on tube, the actual switching mechanism was up in here. So what I could do on this one is I could come up here with these things, and I could set when this thing hit a certain angle, when it tripped my switch and when it didn't trip my switch. So this pressure switch has the ability to do what? We can adjust this one. So let me go this way. That way. This was actually on a pressure gauge. We use them to sense pressure. Yeah, in fact, I'm sorry. This is where it used a mercury switch, by the way. And so when I come up here and hit my trip point, you see the switch change? So that would actually do the switch right there. But I get the ability to set the actual switch point. I'm trying to do it with my fingers, but you actually have to do it down here. So we have bellows. We can use bellows to make pressure switches. They can be adjustable. They don't have to be adjustable. We use diaphragms. So this pressure switch right here. So the switch would actually mount here on the back. So this is where the switch would be. And then there's a bellows in here. So what happens when pressure would come up here, it would cause the bellows to expand and cause this to go out. And then when you left the pressure off, it would go back in. So this is a bellows type. I'm sorry, this is a diaphragm. This is what we call a diaphragm vacuum switch. I mean pressure switch. This is a bellows type, and this works just like the bellows on a hand organ. Is that when I put pressure in it, it's going to cause this thing to spread out. When pressure goes away, it's going to cause it to compress, right? Also, we could use these. We can use these to measure a vacuum. So it's at a certain spot, but if I put a vacuum on it, what is it going to do? It's going to cause it to compress. If I put a pressure on it, it's going to cause it to expand. So this is the sensing element. Is this analog or digital? This is analog. But I could very easily put so normally a lot of our sensors, the sensing element itself is analog. The sensing element itself is analog, but we can combine this with a limit switch, right? You understand? And then when it expands out, the switch hits it and it opens and it closes, and that would be digital. So a lot of your analog sensors, we combine it with another sensor to turn it into a digital sensor, right? Or I could take this and hook it up to a linear pot, and then I could have this move the wiper on the pot, and now I've got an analog sensor. So a lot these sensors right here do not develop. So what is the sensor supposed to do? What it's supposed to take a what? It's going to take a physical quantity and convert it into an electrical quantity. Well, how in the world is this going to give me an electrical quantity? It's not. But I could take this and combine it with a limit switch and come up and seal it up and call it a digital pressure sensor. So I don't know the limit switch is in there, right? You understand? But it would be digital. Now, my sensing element is sensing the pressure, and my digital limit switch, when it hits it, would be what? That would be digital. And if I could adjust the height on the digital sensor, on my limit switch, then I would have the ability to adjust what we call the threshold or the sensitivity. So there's bellows, guys. Very easy to understand. To me, it is. So our pressure sensors can either be analog or they can be digital. Usually the sensing element itself for pressure is going to be analog, and then we run it through some type of digital conversion if we need that. The Amatrol line has both an analog and digital pressure sensor on it. So when we go over here and look at the, guess what? In terms of what they call a helical Bordelon tube. So instead of being in the shape of a C, it's in the shape of a spiral. And what that thing does is that, I can't draw it, guys. So it would be in the shape of a spiral. And then what happens is that this guy will try to uncurl, right, when we put pressure into it. And that would still be a port on. RFID, I say that backwards all the time. Where do you run into these guys at? At store. You know, I think I explained that the other day. So these guys don't have batteries. They power up off the electromagnetic magnetic induction of the actual transmitter. And then once it powers up, then it sends back something that can be identified, right? Like I said, this is becoming real popular with even instead of people swiping their badges, this is becoming popular with companies where they put an RFID circuit inside their badge, and these people just walk through. All they got to do is have their badge. It's just like a lot of your new cars. Some of your new cars don't even have an ignition switch on it. You got a push button, and you don't even have to. You got a little transmitter in your pocket, and when you're in there, you have to be so close to your car for the push button to work. And what's nice, if you leave your car running and you get out and walk off, once you get past a certain range, what will they do? Shut off, which is good or bad. I guess it'd be hard to. Temperature sensors. Temperature in manufacturing, keeping up with temperature is really, really important. And we have a thermistor. And I don't know if we got any temperature sensors on the line over there or not. We might. But thermistors, these are a digital, these are solid state devices. They vary their resistance to water. Temperature. They've got to be externally powered. So these guys will always have 3 wires going to them, right? 2 for power, 1 for output. You can get them as what we call negative temperature coefficient or positive temperature coefficient. So negative means the ohm value decreases with temperature, and positive means the ohm value increases with temperature. We've got some of these here. I'll try to get it next class. Bring them over here. All we got is the negative temperature. So when we heat these things up, we'll see their resistance goes down. So this would be one of those guys we would have to use a Wheatstone bridge on, right? Thermocouples. This is what's in your oven. Thermocouples produce a voltage proportional to temperature. They have a accuracy range between 0.1 and 0.5, depending on the type. These guys, since they produce a voltage, they don't have to be powered, right? You understand that? So these guys produce a voltage that's proportional to temperature. Uses junctions of similar metals. We got one of these. Let's see if I got one of these. They use them on furnaces. Yeah, you got a furnace at your house. We call it a gas furnace. Well, I mean, electric furnace. It's real important, you know. If you're a baker, when you set temperatures, you want the temperatures to be right. So the problem with a thermistor is they're really accurate over a short range, but over a long range they have a pretty good error. So thermistors we use in our. So if you got a digital thermostat in your house, it uses a thermistor. But it's pretty accurate because the range of temperatures at your house is relatively narrow, right? You understand? So what's the coldest you get your house? And what's the hottest you get your house? You're talking about 70s and 60s, right? So in the wintertime, I like to sleep in a cold temperature, but still my house never gets colder than 60 degrees. And the hottest it gets when the air conditioner's running at 75. So we're talking about only a 15-degree span. Over a 15-degree span, a thermistor would be extremely accurate. But if we actually looked at a positive temperature coefficient thermistor, if we looked at the voltage, the actual resistance versus temperature, it would come up here and it would look like this. So that means if I try to go over a real long range, then we're going to have a problem. But if I was to come in here, just go over that little old range right there, that's pretty much well a straight line. Y'all understand that? So over a short range, themistors are great, and this is why we use them in thermistor in our house. But if I wanted to get the temperature of steel up to 2,700 degrees, then by George, I wouldn't use a thermistor. So we use a thermocouple. If I want to go in there and I want to bake something at 350 degrees on my oven, I'm not going to use a thermistor. So your oven has a thermistor, has a thermocouple. And it's a little wire that runs around the top. You can't see both metals because the way they make. So basically it's in a tube. And then they have both metals, and then they surround this with ceramic. And then out at the very end where they come together, then that's where they'll touch. And then that's where you have your thermocouple at. And in dissimilar metals, so anytime you join two dissimilar metals, then if you heat them up, they produce an EML. And dissimilar metals are metals that don't like each other. And that's why they're welded together. So thermocouples are really great. The only problem is you got to maintain, and I don't know if I've got, in the sensors class, we'll get into a lot more detail and tell you the different types. They're given letters like J, K, and each letter designates what metals they actually use to make it, and also the temperature range that those things are designed to work in. So I don't know what's used inside your oven or not. That would be something we'd have to think about. But these guys actually produce a voltage that's proportional to temperature. Then we have what we call RTD. You got a water heater, especially electric water heater. These are the units that's sticking inside the water that's measuring the water temperature. These guys, we know what determines the resistance of a conductor. Yeah, size. Material. Length, good. So that means if I've got I could take a bunch of wire, I could coil it together, make it, because that's the only reason, that's the only way it gets this resistance if we use a bunch of wire, right? Very thin wire, and then I put that sucker in a hot water. The resistance goes up with temperature and goes down with cold. So the hotter a conductor is, the more resistance it has. The colder it is, the less resistance it has. And so that's why they run these things called superconductors. That first of all, they don't use the metals; they use a graphite type material, and they run it as cold as they possibly can get it. As cold as they can get it. So this is one big reason they don't insulate power. They don't insulate the big power lines up there. The power lines are not insulated. And of course, it saves a lot of money, but also it allows us to run more current through them, because if we insulate them, then the ampacity goes down, right? You understand? A 14 gauge wire, if you looked up on a chart at 25 degrees centigrade, so if you ever look at a resistance chart for wires, it's going to be given at a temperature. It can handle about 32 amps. But if we look at NEC, National Electrical Code for wiring, they rate a 14 gauge at 15 amps. Because this is uninsulated in free air. So as soon as I put an insulator around the conductor, what happens to the ampacity? It goes down, because now the wire is going to get hotter, right? You understand? Plus all the other things. Well, it is, because what they're doing is they realize over time where these dang wires run through. So where do they run the wires for housing at? Where's all that wiring running at? In the walls. On the other side of the insulator, through the ceiling. So up in your ceiling during the summertime in Alabama, we're talking about, 100, 120, 130 degrees. So what they've done is they've dye-rated that wire is for all these situations. So that means whether you live in Alabama or whether you live in Hawaii or whether you live up in the north, if they rated it 15 amps, then that's going to take in just about every situation you could have in a normal house. Right? You understand? But if you go into Bill Gates' houses, they're going to have to do something different because that house is so what? Big, because now they're going to have to deal with lean. So in a standard house, 15 amps for 14 gauge wire they've dye-rated it or decreased it a lot because they're taking into consideration just about all possible situations that this will run in a house, right? You get into commercial wiring, it's going to be a little different. So RDTs, all these are is just a bunch of wire rolled up on usually a ceramic core, and then they put it inside some type of metal enclosure to make it solid, and then they stick that sucker down in there, and it changes its resistance with temperature, and it's very, very accurate too. So if you've got a water heater or an electric water heater at your house, it's going to have temperature sensors in there, and by George, they're going to be RDTs, I guarantee you. So if you took those things out and tore that metal tube off there, all you'd see is just a bunch of turns of really fine wire. In fact, I've got one here. This came out of my heater. It went bad. I know I saw it. Well, I've got it packed together. So this was the temperature sensor in my unit in my house. And it had a bimetallic strip in it. So there's the bimetallic strip right there. So a bimetallic strip, the way it's got two metals that are bonded together, and then each metal has a different coefficient of expansion. The coefficient of expansion depends, so all metals, when we heat them up, they expand. And when we cool them down, they contract. Well, different metals will expand at different rates and contract at different ways. So if we come up here and bond these things together, then what happens is that if we put them right, then what happens is it'll do what when you heat it up? It'll come up here and literally beam. And this is the way a lot of circuit breakers work. So this right here is a bimetallic strip. And then this right here this is an RDT right there. It's nothing but a wire. Bunch of turns of wire. That's all it is. A very small gauge wire. That's what's going to trip this switch. And then the bimetallic strip is going to switch the other. So this came out of the actual firebox. And so this guy here right here is bad. But that has both a bimetallic strip. It's got both a bimetallic strip and a RDT. And the last one, which is very, very popular, infrared. Used to when they was checking out these vents, is they'd get a big old ladder and they'd climb up and they'd have a gauge that looked like a meat temperature gauge. You'll see those, you can buy them at Walmart. These were basically the same thing, and they would take that and they would literally insert it inside the vents. And then they'd have to wait a little while because it takes a little while for those things to respond. Now what do? If they wanted to measure the temperature of that vent right there. They got this little thing in their hand, and they point a beam at it. They point a laser beam at it. The laser beam is not the sensor. The little laser in there is to aim it, because you got to aim it almost perfect to get an accurate temperature. And then it's just measuring the infrared that's coming off. So infrared is very, very important. It's an electronic circuit is required. Measures the wavelength of the light to be calculated. May be affected by reflection of water. Of the body, temperature to be measured at a distance. So these guys are very, very popular now for measuring at a distance.
Like you're saying, I think though, they used to run race cars, tires,
Check tire temperature.
What you said, I think it's just a laser, and that's just guided.
That's just an aimer. So it's like these people that have laser sights on their rifles. That's all. Those laser sights are gonna kill anybody.
So,
No, the laser's not measuring. It's the infrared sensor. But the problem is, if you're off a little bit, you're not gonna be measuring what you're interested in. And this is the problem we have with these things. Is this guy right here? They can be affected by reflection from other bodies. So to keep it from getting at other bodies, you need to aim that thing. So either you're going to do it with a scope or you're going to do it with a laser.
so if you have one of these that don't have the laser on it, you just point it to that table.
You don't know what you mean.
Well, it's this table.
Well, yeah, but you don't know what part of the table you're in.
What kind of beam does it send out?
It's an ultraviolet, it's an infrared camera. That's all it is, an infrared detector. It don't send out a beam. It just looks at the picture coming in.
What I was wondering.
So it would be saying like a regular camera. So I got a regular camera. You say, what does it send out to take a picture? It don't send out anything. It takes the light coming into it and exposes something to develop a picture, right? You understand that? Yeah. So a camera don't send out anything. And that's so instead of me setting up all these sensors back there that it senses all these colors, I have sensors that only see what? Things that are in the infrared band. So the sensor don't send out anything, but the problem is that you don't align that thing perfectly. So when I take a picture, I can take my camera up here and I can put it up here and I can say, well, I'll take a picture of you, Eric. And what would I probably end up with? No telling. I might take a picture of your belly, but if I come down here and aim it, then I know I'm taking a picture of you. So I can put a sight gauge on my laser sensor and I can come up here and do that. Because if I'm off a little bit and I'm trying to measure tire pressure, I might be a little bit on the road or something like that, right? And then not my tire pressure, my tire temperature. So those things most of them have laser beams on them. So and the laser beam is not doing the measuring. All the laser is doing is what? Is aiming. That's all it's in there for.
Well, I've got a couple of laser measurement things.
Yeah.
So you're saying it's the same thing?
Well, it's looking at reflective. What those things are a little different. Those things are measuring the time it takes for it to send out a pulse compared to the time it takes to come back. And it uses that to measure.
Well, I used one for years and they're very accurate.
They are.
But the first ones we got were like $400.
Yeah. Now I got one with a set for Craftsman, and I don't know what it came with, but it was really neat. I got 2 sheds in my backyard, and I wanted to build a top over the middle where I parked my lawnmower. So to do that, I had to have the 2 sheds aligned perfectly, and that's exactly what I used. I used those laser measures. It was really cool. Solenoid, y'all okay with solenoids? We got solenoids all over the place. So what does a solenoid do?
Solenoid converts electrical action.
Well, we got a lot of stuff that does that. Solenoids are special. Into a linear motion, into a straight line motion. Does it do it in 2 directions? No, it only does it in 1. So I either put a magnetic field around this thing, which causes the program to either suck in or extend out. And when I take the current off, what would happen?
I'm thinking about a solenoid on the Chevrolet starter.
Well, it's got to have something too. That solenoid only engages the starter. That solenoid does not disengage the starter. What disengages the starter? The spring disengages the starter. So solenoid only generates force in 1 direction. We're going to have to depend on something else to do what? To bring it back. And normally we usually use gravity or we use springs. So you see some relays that use solenoids. All relays use solenoids. But that's what the linear motion does. It opens or closes contacts, right? You understand that? We have some that you have to mount vertical because it depends on gravity to open them up once you energize it. A lot of your relays have springs on the armature or the plunger So when you de-energize it, it'll cause them to open up. Electric motors, y'all. This should be a. In fact, it's time to go. No, this class gets off at 1:30, right? I keep getting my other class confused with this. So, so electric motors. So this would be a review of what we went through in motor control. Everything here we talked about in motor control. We have two categories of motors, electrical motors. So what's the difference between a rotary actuator and a motor? So first of all, what's an actuator?
Actuator, that's
Converts energy into motion. That's what an actuator does. So literally a motor is an actuator, but we use two different terms. So a motor is a rotary actuator, but we don't call a motor a rotary actuator, we call it a motor. But we have what we call rotary actuators too. What's the difference between a rotary actuator and a motor? A rotary actuator has limits. It will only rotate a certain distance, period. Usually less than 360 degrees. So a rotary actuator has set limits. A rotary actuator has a stroke. A motor does not. So a motor can make unlimited rotations, right? You understand that? With no limits. We determine the limits of a motor. The limits of an actuator is controlled by something mechanical, rotary actuator. That makes sense? Everybody okay? So motors. So these are motors. So we have hydraulic, we have fluid power motors too. And we have rotary fluid power actuators. So we got a couple of actuators over here. We have some electrical rotary actuators, and you'll see all of them have limits. They're going to stop somewhere, right? Where a motor has no limit. It rotates with unlimited rotation. So we have two categories of motors, DC or AC. And within these categories, we have several other types. So in the DC, we have shunt motors, series motors, and compound motors. We have stepper motors, and brushless motors. On the AC side, we got single phase and three phase, right? You understand that. And inside the single phase, we have capacitive start, capacitive run, split phase, and what we call shaded pole. And then three phase, we have Y delta, we have delta Y, and we have what we call a wound rotor motor. And then we also have what we call synchronous motors, either single phase or three phase. Which ones do y'all don't know something about? Stepper motor, I don't have my thing in here. So a stepper motor is, and I got an animated GIF I'll show y'all. So this is a DC motor. So this is a stepper motor. Nope, don't have it in here. Dang it. Here we go. This is a stepper motor. This is doing what we call half steps, and we'll talk about this later on. But what we do with a stepper motor is we rotate the stator, the stationary field, or the outside field. We move it in steps. And then the rotor is nothing but a magnet. It's a permanent magnet. So what's the rotor doing? All it's doing is aligning with the field, right? But notice what's the motor doing? Is it running smooth or is it running in steps? Now we can make it appear to run smooth. Well, it's called slew mode. So if I could rotate the output out at a speed where the rotor can keep up with it, and the maximum we can run it without it starting slipping, that's called the slew mode that we run the motor at. And we can do what we call half steps. You see how it's doing half steps. Can you see how it's doing half steps? So what it's doing is leaving two of them energized at the same time, and what it does is line up in the center. Some stepper motors let you do half steps. Some of them let you do what we call micro steps, which we'll look at. So what determines the resolution or the accuracy will be the number of steps we have per. So right now, how many do we have? So if we start at the top, 1, 2, 3, 4, 5, 6, 7, 8. So what happens is that I would say, how many degrees in a revolution? How many degrees in a revolution? 360. So what would that be? 360 divided by 8? 40. Yeah. So it'd be 40. No, it'd just be 40, right? What's 8 times 4? Okay, so 45. Yeah, 45. So that means each step would be what? 45 degrees, and that would be the accuracy of my stepping motor. So if I want to get better accuracy, what would I do? I'd add more steps. And how do we add more steps? Well, we add steps on the outside. Right? You understand? So the more steps I put, the more accurate the stepping motor would be. A standard step size on without doing what we call half steps is 200 steps per revolution. So if I got 200 steps per revolution, that's going to be 200 divided into 360. And what's that going to be? One point something. So now we're down to 1.5 degrees. If I half step it, then that's going to be 400 into 360 degrees. So now we're talking about a lot less than 1 degree per step. So if we get this accurate, and that's what's on the carousel over there, is a stepping motor. It's really, really accurate. I don't know how many steps that is. What we probably need to do is, and how do I change directions, is I would just change the sequence of the steps. So here we're stepping clockwise. All I have to do is change the sequence of the steps, and then these things will run backwards. But what you got to understand, these suckers have got to be electronically controlled. They've got to be electronically controlled. So this is the parts of a regular DC motor. We have the field, we have the armature, we have the commutator on a regular DC motor. These are not the special motors like stepping motors. Stepper motors and brushless motors are in a field by themselves. This is a standard DC motor, whether it's a shunt motor, whether it's a series motor, whether it's a compound motor. This is the basic makeup of the DC motor. So we have the field, right? The field can either be a permanent magnet, or it can be a electromagnet. This is showing a permanent magnet. And by the way, this is not true, but you'll run into this. It's just like people using the term ground. How often have you heard that used correctly? You hear it used incorrectly all the time. But as long as you understand what it is, then we have no problem. If you don't understand what ground truly is, so a lot of times people call a common a ground. And that's no problem with me. I have no problem with that. But I make sure that you understand what a true ground is and what a common is. Okay, you understand that? So notice this guy right here, when he put this together, it's a beautiful animation. But he called this a stator. And in DC motors, it is not the stator, it is the field. It's called a stator in an AC motor. So an AC motor, we call the rotating part the rotor, and the stationary field, we call that the stator. It's the stationary field. In DC motors, the stationary field is called the field. The rotating field is called the armature. And that's true terminology. Does this bother me? Nah. Would it bother me if y'all don't use the right terminology? Probably. So I will probably correct you. So the armature is the rotating part. The stator is the field is the stationary part. And then what makes them rotate, guys? Yeah, but we can't say magnetism because nothing rotates if we just put a magnet field on there. So if I was to come up here, plus and minus don't, and so if I came over here and had two magnets, and I put one right here, and I put this one on the spool, and I put that magnet right there, and this was a north, this was a south, and then this right here would be a north, and this down here would be a south. What's it going to do? Is it going to rotate? Is it going to rotate? No, it's just going to sit there. So what makes a motor turn? One of these fields has got to move. One of these fields has got to move. So one of these fields are going to have to swap, right? You understand? So if this was an electromagnet, I could get me a little switch out here. And I could be switching them between negative, positive, and I can make this thing rotate. I can sit there and switch it like that. And if I swap fields, and this guy right here has the same polarity, then now all of a sudden I'm repelling, and what would it do? It would spin. Of course, I would need to do something about the direction, right? You understand? Because right now we wouldn't know which way it would spin. So I could come over and I could flip that switch, but that's me flipping the switch, right? So what do we do on a DC motor? Well, we let the motor flip the switch. So if the motor's rotating, why not let the motor keep swapping the fields, right? If the motor keeps swapping the fields, then what's it going to do? Now I've got a field that's in motion with a field that is stationary, a field that's in motion with a field that's stationary, and now the motor's going to spin. So to make an electric motor spin, one of the magnetic fields has got to do what? It's got to move. So that's what the commutator does. So that's exactly what this commutator does. What's it constantly doing? It's constantly switching the field. It's constantly making, if this is a south right here, it's constantly trying to make this right here a south 2. If it makes this a south 2 all the time, what's it going to do? It's going to keep spinning. But when the north comes back around here, it's going to switch it back over to a south, right? You understand? So it's going to be a north up in here. This is a south. It's going to pull it in there. As soon as it gets on there, it's going to switch it to a south, which is going to make it repel it and switch it off. So what does the commutator do? It's constantly switching the field on the rotating part. So what we do on a DC motor is we let the rotor do what? Or the armature switch the field, which causes the motor to rotate. If the commutator wasn't there, the motor would just do what? It just freeze. So on a DC motor, on these standard DC motors, the armature has got to be electromagnet. It's got to be. This outside magnet, since it's a stationary, it can either be an electromagnet or it could be a permanent magnet. Now, what's nice about the stronger you make the field, the more torque the motor has. The weaker you make the field, the less torque the motor has. So if I've got a permanent magnet motor, I can't control the torque. The torque will be controlled by how much current we put into the armature. If you put more current into the armature, it speeds up. But let's say I want more torque at 60 hertz. I mean at 30 RPM. Well, you can't do anything like that with a permanent magnet motor. So the torque is set by the speed, right? So the faster the speed, the less torque the motor has. Okay, you understand that? But if I can control the field, then I can control the torque. So a motor that's got a wound field, not only could we control the speed, we could also control the torque. Does that make sense? So a permanent magnet motor, we can control the speed, but we can't control the what? The torque. So we have a lot of permanent magnet motors. What's all the DC motors in your car? Except for the starter. The starter is not a permanent magnet motor. The Starter is a series motor. But your windshield wiper motors, your door latching, those are all permanent magnet motors. All the motors over here are permanent magnet motors. Are you okay? The brushes, these are devices that transfer the energy between our power source and the rotating rotor. And then the way we reverse it, we change the rotor on. The armature, the rotating part. So what's the problem? What's one of the problems you see with the DC motor? Okay, so where do we have our most problems? Besides for burning the motor. Yeah, brushing wear. And the commutator gets dirty. So the commutator, as the brushes wear, it gets all kind of goop in there. So DC motors they usually require maintenance. So we have to go in and clean the commutators and change the brushes out every once in a while. If you got a good drill, it gives you the ability to do that.
I got one I've had for 40 years and I've never cleaned it.
Yeah, but you got to take in consideration how often do you use your drill?
There it is.
You don't use it that much.
No, it's a big old drill. It takes a man to run it.
Oh yeah, I got a big old Craftsman that's got the side handle on the dang thing. That's what will kill you if you let it. So it's got the third handle, so you're holding out here. So it's a half-inch drill. Of course, a lot of your new drills will do that. This is what we call a separately excited motor. What we call they're calling it a common source shunt motor. Both of these they call them shunt motors. Normally what you'll hear, so this is technically called a separately excited shunt motor. This is called a common source shunt motor. Because notice on this one, so on this one I got two leads coming out of the motor. And that's it. How do I reverse this thing?
I missed this the other day, switching.
No, that's a three-phase motor. Change the voltage. So let's say I came up here on this one and I put this and this and it caused it to turn that direction right there. So this is the symbol by the armature, by the way. So they draw a circle and they put these little things right here representing the brushes. That's the symbol for the armature. And let's say I came up here and changed the polarities on this. What would happen to the direction of rotation? It wouldn't change direction. It won't change direction. Unfortunately, we're not over there in the lab. To change the direction of rotation, you have to change the relationship between the armature and the field. If you swap both of them, and we did this in motor controls, if you remember. We went over there and set up a DC motor, and I swapped it around, and what did it do? If I changed both the field, and I changed both the field and the armature, the dang thing didn't change direction. So to change the direction of a DC motor, you have to change the relationship between the field and the armature. So you can reverse one, but don't reverse the other. So if you can reverse the field and leave the armature alone, or you can reverse the armature and leave the field alone. So a shunt motor is non-reversible. A common source shunt motor is non-reversible. Unless they give you a plate on the side where you can literally take it off and swap them from inside. Some motors give you that ability to do that. A separately excited motor, we can do what with that? We can reverse it with the armature or we can reverse it with the field. Now the problem is if we lose the field and the motor's running, it will run away. We're not going to talk about why in this class. We talked about it. So normally, the normal way to reverse a DC motor is to change the connection on the armature and leave the field alone. I was over in Germany, and those guys over there, you could tell they had a lot to do with motors. You know, they thought you could change either one of them. You can change either one of them. But the problem is, if something fails in your reversing circuit, then and it's a shunt motor, it could run away. If something fails in your armature circuit, then the motor stops. So what would y'all rather do, run away or stop if something fails? Yeah, you would rather it stop, right? It's just like in motor controls, we have, in PLCs, we have that symbol right there, and then we have this symbol right here. Well, in motor controls, if you remember, your stop button was a normally closed push button. And this is one of the hardest things we have to teach in PLCs, especially after they've had motor controls. So what they want to do is when they hook up their PLC, when they program their PLC, they want to program this like this. Because this is the way they learned it to use it in motor controls. That's what they want to do. Well, the problem is, this is what we call an examine if open. So what happens is you come up here and you fire up your PLC and you hit this button 100,000 times and nothing happens. Because if the switch is open, right, you understand that? It's true. So what we have to do over here, my push button has to be open. Right, you understand? So to get this right here, so if it's open, it's false, examine if open, right? You understand that? And if I close it, then this right here would indicate open. So what we have to do, and what do we want to use for a stop button? Do we want to use a normally closed push button or a normally open push button? So what does industry require for a stop button? A normally open or normally closed? Requires a normally closed. Because if a wire breaks in my control circuit, you understand, now I can't stop it on my PLC. Because your PLC is not, even though we draw it in series, it's not in series, it's coming into a port on a PLC, right? You understand? So if I use a normally open push button and it fails, I can't stop it. But the problem is, what we have to do is in a PLC, if this is a normally closed push button out here, we want to put examine if closed, right? You understand? But in my PLC diagram, I have to draw it as an examine if closed. So examine if closed, this is closed, so this right here would be true all the time. But it looks wrong because in motor controls, we have to use a normally closed. In PLCs, we're supposed to use a normally closed. But the problem is they want to draw it like this, and now their circuit don't work if they use a normally closed push button. If they use a normally open push button, it works. And we have a problem with the 1100 PLCs over there, or the 1000s, because they don't have any normally closed push buttons on the trainer. So that's right. So if the motor fails, if something fails on the motor, we don't want it to run away. We want it to do what? Stop. So if you lose your armature circuit, what does the motor do? The motor stops. If you lose your field circuit and it's a shunt motor, what could the motor do? Yeah, it could run away. It could run away because the two fields have to counteract each other, which is really, really interesting. So this thing works off something called counter EMF. The less voltage we have in the field, the faster the motor has to run to counteract the field is what's happening. And so yeah, a shunt motor just by the residual magnetism in the pole pieces, a shunt motor would try to run away. So how do we normally reverse these things? Do I have this fit in here? So if we change the armature current, the speed varies with the armature current. It varies inverse with the field. So if I wanted to run faster, I would lower the voltage on the field. The problem is if I lower the voltage on the field, the torque goes down. But if I can use these two things together, so if I could raise the voltage on the field, the motor slows down. But if I raise the voltage on the armature at the exact same amount, then we create more torque at the same speed. So what's nice about a separately excited motor is we can control the speed and we can control the torque. And we can also do what with it that we can't do with a shunt motor. We can do what? We can reverse it. We can't reverse a true shunt motor. Unless they put a plate on the side of the motor that lets you do what? Open it up and they bring your bring your windings out and you can swap one over. Permanent magnet motors, these guys are all over the place. So I need to put that. So normally how do we change direction on a DC motor? We don't change the field, we change the what? Armature. Permanent magnet motor, these things are they're fractional horsepower motors, but they're very, very cheap to make. Got good speed characteristics. They're very low horsepower rating. And of course, it's obvious how we reverse these things. There's only one way. So it would be awful. So y'all know your locks on your doors do not use solenoids. And why is that? Yeah, you'd be able to lock them, but you'd have to pull them up. So they have little motors on them. And so you're reversing those motors. Now we limit the rotation of the motor, but we don't limit it with the motor. We limit it with electrical, right? Understand that? Yes or no? Series motor. This is what your starter on your car is. A lot of hand drills use this. Has great starting run torque, very poor speed regulation. These guys here can run off of AC or DC. One reason is this field right here says there's so much current running through it. There's very few turns of wire. I don't know if everybody took a car starter apart, but the field has almost no turns at all because what we're trying to do is trying to create a lot of current, right? Understand? So these things have a very low what we call X of L. So that means they don't change a lot with AC. The problem we have with these shunt motors is we have something called X of L, which sets the AC opposition of the motor. And the X of L is equal to 1 over 2 pi FL. This don't really make any difference. But you can see, and this is ohms, this is opposition. If that frequency goes up, the opposition goes. I mean, the wrong formula. X of L is equal to 2 pi FL. So you can see if the frequency goes up, what happens to the opposition of the motor? It goes up. So that means if I put AC on this shunt motor, we would get no current in our armature and we'd get no current in our field because each one of them would have so much opposition. On a shunt motor, these guys here are designed. What determines the strength of the field is how much current you put through that thing. So what you would find is that the armature on a series motor has very few turns of wire, and the series field has very few turns of wire. So that means their X of L, is this guy L here is very, very low. So if L is very, very low, that means we can put frequency on it, a low frequency like 60 cycles, and the X of L would not vary enough to cause a lot of opposition. So a series motor is called a universal motor, which means we can run it on what? AC or DC. So a lot of vacuum cleaners have series motors. A lot of hand drills have series motors. And what's nice about this is they have a lot of starting and run torque. But what usually happens to your hand drill, you got your hand drill up in the air and you're turning it, right? As soon as you put it into something, what does it do? Slows down. But these new motors, by George, what happens to the torque? No, not in a series motor. As it slows down, you get less counter EMF. If you get less counter EMF, you get more current flow. If you get more current flow, if you get more current flow in the field and the armature, then the torque of the motor goes up. So on these, if you try to load them, their speed drops down and torque just goes way up. So what happens to that big old hand drill if it gets bogged down? It's gonna break your arm, because now the motor stops altogether. You get no counter EMF. You get maximum current flow through both those fields. So you got maximum both current flow on both your magnets, and you get maximum torque. So these dang hand drills, you got to be careful with. I mean, they will what? They will hurt you. You get some of these 20-volt drills, got all that voltage out there. They'll hurt you. So your starter motor in your car's series motor creates a lot of torque. We're not concerned with the speed. We just want it to turn that motor all over even in the winter time, right? You understand? A lot of hand drills use series motors. A lot of vacuum cleaners use series motors. I think I've got a compressor that fell apart and used a series motor. So these are very, very popular motors. If we're not concerned with speed, if we need a lot of torque. And what's torque? Torque is a unique type of power. What is torque? Turning, yeah, torque is twisting. So torque is a twisting power. It is a turning power. So the only place we use torque is something that's turning, right? You understand? So the more torque you have, the more turning power you have. And the less torque you have, the less turning power you have. So torque is a twisting power. So you got a torque, anybody got a torque wrench? What do you use a torque wrench for? Yeah, to check, yeah, yeah. This is a compound motor. I know we're fixing to live on. So a compound motor basically combines a series motor and a shunt motor. So it doesn't have as good speed control as a shunt motor, and it doesn't have as good torque as a torque motor, but it gives us both characteristics. So it has better torque than a shunt motor, and it has better speed than a series motor, which is pretty neat. What's that? No, these are usually series motors. Or it depends. A lot of times they compensate for the low torque of a shunt motor. They compensate it with a gearbox. They compensate with a gearbox. And they're talking about moving them toward what we call brushless DC motors, which we'll look at later on. So from what I understand, a lot of your new, very expensive hand drills use brushless DC motors. So next class we'll show y'all pulse width modulation. Hopefully we'll figure out what's wrong with that. And then, but it'll probably be Friday before I can call that I have any time to sit and talk to the guy. Try to come in here and try to get it fixed.
That would happen.
syncing and sourcing is the way we connect sensors and the way we connect outputs. So when you hook up these sensors, and I know it's time to go, guys, but when we hook up these sensors, what we like to do is we like to take our sensors. So let's just use push buttons as example. Okay, so I got push buttons. Then we got all these push buttons. So in motor controls, what we would do if over here is we would take all our sensors and connect it to what we call L1. And then when we got over to the other side, we would take all our outputs and we would connect them to L2. So for my outputs, this is a common. And for my inputs, this right here would be the common for my inputs. So a common is just something that so a lot of times we consider the common to be the return, but that's not necessary. A common is just a common connection where you connect multiple things together, right? You understand? Now, what is this? What is in DC? What is L1? Is it plus or is it minus? Maybe it's whatever you decide. So what we're doing on a PLC is we've got to complete a circuit. So I've got to complete a circuit. So in DC, we've got to have a minus and we've got to have a plus. So I can take all my inputs over here and I can take that input and I can either connect it to, I can make the minus the common or I can make the plus the common. Well, what do I need to get current flow? Well, I got to get a plus somewhere, right? So I got to come over here somewhere and put a load. I'm going to just put a resistor there. And then all my loads would have the plus as a common. Okay, you'll understand that. So when we talk about, so when I press this button, it's going to put a minus over here, and then this is connected to a positive common, right? You understand? Okay. Now in syncing and sourcing, anything that provides a minus, we call that syncing. Now what's it looking for though? So this load right here would have to, it uses a positive common, so we call that sourcing. So on PLCs, if we got a syncing sensor, it's got to be hooked to a sourcing input. If we got a sourcing sensor, which means it's going to use a positive common, it's got to hook to a syncing input, right? If I've got a sourcing output, which means it's going to provide the power, then my devices have got to be hooked to the negative. So a sourcing output has to be hooked up to a syncing load, right? You understand? So what we're talking, and this only comes into play on DC. So on PSET PLCs, and this came from digital, by the way. So if you take digital, we'll learn more about syncing and sourcing. And they carried this over to PLCs because they use transistors and they use digital logic. So anything that uses a minus, uses the negative as the common, those are syncing devices. Things that use a positive as the common, we call those sourcing. If I've got a syncing, so when you go out, if you go over there and you get on the, when you buy your fixed PLCs, that's usually set in for you. The Allen Bradley you can select, and we'll go over their next class, remind you and show you all that. But so the Siemens PLCs, the inputs for those PLCs are syncing inputs. So that means if I went out and bought a syncing sensor and hooked it up to those syncing inputs, it wouldn't work. No, I hadn't. But if I bought she bought a sourcing sensor, and I figured out. But if you buy, so if I've got syncing inputs, I've got to have all my sensors. I've got to be sourcing sensors, right? So, but they call them this. So an NPN sensor is a syncing sensor, and a PNP sensor is a sourcing sensor. So they might say syncing, but that's what you got to know. So if I buy an NPN sensor and I've got a syncing input, I've screwed it.
Things that another place. I can't correlate that to anything. Is that just something dangerous?
Well, the sourcing makes sense because it's providing the source.
But now sinking, I always think about a ground or.
Well, it's not, it's just the minus. So in digital, it's going to be the common. The syncing output's going to connect it to common, but in PLCs, it's swapped over where a negative common, a negative. So in PLCs, what's common? You got a power supply, it's got plus and minus. It's what you determine is common, right? So that okay, syncing the source.
Yeah.
So all our sensors over there are sourcing. So that's why you see every one of them connected to plus.
Now, wait a minute. What about the other line?
I think those are sourcing. We would have to, those lines you have the ability to set up groups of outputs as either synchronous. But they set them all the same way.